Good morning, everyone. My name is Seongkwang Kim from SDS. This is a joint work with KAIST and Songshin Women's University. As previous presenters explained MPC in the head paradigm very well, we briefly recap the MPC in the head paradigm and introduce a MPC in the head based proof system. In 2007, Ishii et al. Proposed a generic conversion from MPC to zero-knowledge proof. Briefly speaking, MPC in the head is simulating a multi-party computation for a relation in her head. So let's have a look. First, prover simulates a multi-party computation of a function f, and prover commits to all the views of the parties, and verifier sends a random challenge. It becomes non-interactive when Fiat-Shamir is applied. And the last, prover opens the challenged view and verifier checks consistency. So BN++ proof system is proposed by Kales and Zaverucha, and the security of BN++ is based on the one-wayness of a one-way function in the random oracle model. BN++ proves inner product by sacrificing technique. If one wants to check multiplication triples xi, yi, zi, such that xi times yi equals zi, then parties make inner product triple a, y, c, such that sum of a, I, yi equals c. Then for random epsilons, then share of alpha I is epsilon I times xi plus ai, and open alpha I and check the delta, check the v. So then the soundness becomes a reciprocal of the field size. From that, there is efficient circuit when in simulating in BN++. First, since small field size has a poor soundness in the BN++ proof system, I know that vol in the head has no such demerit. So we use a large field arithmetic of size like such as delta lambda, and small number of multiplications makes signature size smaller, and linear maps are free. There are some techniques for BN++ called repeated multiplier. If some multiplier is repeated, then signer can save the signature size. For example, if x1 times y equals z1 and x2 times y equals z2, then y is the same multiplier, and signer can save the signature size. The last one is known output share. If the party knows some output of a multiplication, then the signer can save the signature size. For example, if y equals x inverse is an S box, then x times y equals 1, and 1 is beforehand known without any computation. So now we introduce our new symmetric primitive, aim. Here is a motivation. Recently, MPC-friendly symmetric primitives are advanced in S boxes on large field and low multiplicative complexity. But however, some symmetric primitives are recently broken by algebraic attacks such as MIMC, Agresta, Jarvis, and Friday, and Chagri very recently. So we target both sufficient security against algebraic attacks and best performance when combined to BN++ proof system. Inverse SBox is widely used in MPC ZKP-friendly ciphers as well as AES because it has high degree and quadratic relations to check, and it is invertible and has nice DC-LC resistance. But we found out that inverse SBox produces many linearly independent quadratic equations. It does not mean AES is breakable. It's just about MPC ZKP-friendly ciphers. In the early 2000s, inverse SBox with n bit input is known to have 5n quadratic equations. In the algebraic attacks, more equations can lead to a weaker resistance to algebraic attacks. So we found some candidates of appropriate SBoxes which have a smaller number of quadratic equations. So there are 4 candidates: Niho exponent and NGG exponent, Mersenne exponent and Gold exponent. And we chose the third one, Mersenne exponent, because they have all the merit we want, and they have no critical demerit. After choosing the SBox, we choose some structure for BN++. So as mentioned before, BN++ has a technique called repeated multiplier, which can reduce the signature size. So let's have a look with serial application of SBoxes and parallel application of SBoxes. Then parallel SBoxes can be applied fully repeated multiplier, but not the case for serial SBoxes. So we can introduce our symmetric primitive aim, which is the composition of all the things before. We chose Mersenne SBox for first time, invertible, high degree, and quadratic relation. And Mersenne SBox is, you might not remember, it's the exponentiation by Mersenne number, which is x to the power of 2 to the s minus 1, which becomes quadratic relation to xy equals x to the power of 2 to the s power. So it requires a single multiplication to check. And we found out that Mersenne SBox for some valid parameters produces only 3n quadratic equations, and it has moderate DC-LC resistance. Not the best DC-LC resistance is not a problem because an attacker can query just only once. So we chose a repetitive structure. So we apply the SBoxes in a parallel. And finally, for the security, we use randomized affine layer generated by XOF, extendable out function. So here is the parameters. There have been some analysis on AIM recently, so we have introduced some analysis and some of our mitigations in work in progress. In July 24th, Fukang Liu and Muhammad Mazun proposed a fast exhaustive search attack on AIM, and it achieves. We we admit that it achieves 10 to 12 bits smaller complexity compared to brute force attack on AIM. So we worked on that. We found out that increasing exponents resolve this problem. The second analysis on AIM is in July 27, Liu, the same person, introduced another possible vulnerability to our team in private communication. He said that setting a new variable w equal the inverse of input leads to an easier system to solve. So it makes 2n variable system, including 5n quadratic equations and 5n cubic equations. But we know that this attack is not practically feasible on AIM, but it may be a possible vulnerability. So to mitigate these problems, we introduce some mitigation work in progress called AIM2. So we will use inverse Mersenne S-box in the first round. So it's like it's an inverse function of Mersenne S-box. And we found that it is more resistant to algebraic attacks. And we will use larger exponents called E1, E2, E3 to mitigate the fast exhaustive search, because fast exhaustive search is based on the low degree representation of the AIM. And we will use fixed constant addition because we use the parallel structure of the first S boxes in the first round. It does not differentiate it well in the AIM version 1. So we want to differentiate the inputs of the S boxes. So we are now working on analysis on AIM2. We do some algebraic attacks, including fast exhaustive search, and we brute force search of quadratic equations, because more quadratic equations makes easier systems to solve. And we find some good, we try to find some good intermediate variables. Is there any kind of variables? And other attacks, very recently, I saw that in September the 2nd, Marku posted on PQC forum, and he proposed a efficient exhaustive search attack, and we think that AIM2 can mitigate this problem, and we will update soon. Other attacks, there's no problem. And performance, for the signature size, it is exactly the same, and signing and verifying time will be increased about 10%. Preliminary version can be found in our website now. So it's the last. Finally, I can introduce the AIMer signature scheme. AIMer signature scheme is a BN++ proof of knowledge of AIM input. So security is based on the AIM in the random oracle model. There are a few advantages. The security of AIMer is solely based on symmetric primitives and has fast key generation because it's just a symmetric key encryption, a symmetric key evaluation, and has small key size and trade-offs for MPC in the head paradigm. And there is randomness misuse resistance. And AIMer has some limitations. Because AIM is newly designed, someone might don't want to use the newly designed symmetric primitive. I understand this can be a limitation. And the second limitation is moderately large signature size, and the third one is quite slow signing and verifying speed. So it is here is performance comparison. The last two rows are about AIMer, but it is not updated to AIM2. So remember it. And signature size is from about 3.8K to 5.9K. You can see that 3.8K is very similar to the bandwidth of Dilithium 2. Finally, we have some remarks. We submitted AIMer to KPQC and NIST PQC competition, and here's our homepage. We are waiting for third-party analysis. As a future work, we will try to prove a QROM security of AIMer and do some optimization on BM++. Thank you. Check out our website.